move through the slides at a pretty good pace just so that we have time at the end for any questions. So I've got about 45 minutes to work with. So without further ado, I'm going to go ahead and begin. So today's topic is why do MSA studies? Before we dive headlong into the studies, which is pretty much what everybody might have come for, I always like to take a little bit of a step back and just talk a little bit about metrology. And metrology is really just the scientific study of measurements. And it's important to note that just because when we talk about these MSA studies today, it's kind of nice to know where we arrived or where we were coming from. So metrology has been around since as long as humans, and what we'll actually find is throughout history, as cultures, as different organizations and societies start to improve, get the Romans and lots of other ancient antiquities, that the evolution of measurements has also changed and grown with that. So it goes hand in hand with a development and advancement of cultures and societies. We can find archaeological specimens and digs where we're finding artifacts that are kind of giving us a clue as to what measurements were actually used during the time. Things like cubit, span, palm, finger, and nail. Some of these might sound familiar, especially the cubit. Some people probably have heard of that term, but not a lot of people really know what it stands for. So in essence, the human body was really the first measurement system. Everybody had different parts on them that they could be easily used as a reference when they're building something or making something. So the cubit is actually just from the tip of your elbow down to the longest tip of your finger. Now, a problem with that is that if I'm a vendor or if I'm somebody shopping at a vendor booth, I'd probably want to find the tallest individual that's selling what I'm after, because chances are I'm going to get a really good deal if they're selling me 2 cubits of some item. So you can see how that could become problematic. Nobody is using a standard or set of measurements. Another thing I like to discuss usually when I do training is this Chinese folktale about the emperor and the elephant. So as the story goes, the emperor, when it came time for his birthday, a lot of the different noblemen and countrymen, the people that were going to attend his party, they always wanted to outdo one another. So one nobleman had a clever idea. He had an elephant and no one else did, so he decided to give that as a birthday present. Well, the emperor and the rest of the entire community was very impressed until the emperor posed the question, how much does the elephant weigh? Well, at the time, there was no scales in China that could actually measure an elephant, something of that size. So as the story goes, it was actually the emperor's youngest son that came up with the technique. They took the elephant and loaded it onto a boat or a small barge. They took it out to water, waited until it sank a little bit, and then they marked on the side of the boat where the water was displaced. Now, getting the elephant back to shore, they took it off and they started filling the boat with stones until it sank to the same level as that mark. Then we could work with those stones to individually measure them, and then we come up with a grand total. So the reason I like to bring this story up is because first, it's a cute story about metrology, and second, it shows that sometimes when you're looking to do a job or accomplish some task, you have to be a little bit inventive in your approach to getting the measurements that you need. Later, this buoyancy principle was attributed to the Archimedes principle. So like I said, the measurement or the metrology kind of world has been moving in a certain direction, and hopefully we're going to continue to move in the right direction. So the French Revolution actually was an important step in the world of metrology, because during the French Revolution, we actually formalized the metric system. It had been around for a couple of years, but it really wasn't, I guess, kind of across the board accepted. So the metric system is a way for standardizing a lot of the different various units of measurement that the world uses. One of the French philosophers said, well, the metric system is for all people and for all time. The big part of this is that if you are buying a bale of hay or a bolt of cloth, you're going to be getting the same size, the same unit, the same weight, whether you're in the rural countryside, whether you're in Paris, or whether you're across the world. So the path to metrology, and pretty much where we are today, it's never finished. It's been a meandering path all the way from antiquity to now. And even now, when we talk about metrology and how it's progressed, we're moving away from analog, meaning if you had a meter that's actually stored in Paris, the kind of granddaddy meter of them all under lock and key, that still fluctuates. Over time, that could make big changes when you have these different international standards all using it. So one example of that, where we're moving away from these analog benchmarks, is the definition of a second. It's 9 billion oscillations of cesium-133. And a fun fact is they're actually working, they found another isotope of cesium that can give us an even finer degree of resolution and accuracy on that. So I think the last one that's holed out right now is the kilogram, and there's 2 different paths that they're working on for that. So if you're interested, look up some of the different articles about the definition of a kilogram and what work they're doing to make improvements. One last thing before we venture right into the MSA, I just have to give a shout out to this BBC documentary called How Long is a Piece of String? Obviously, we're not going to have time to watch any of that today, but if you're interested in metrology like I am, and you've got a little bit of time to kill, this is actually a wonderful documentary where it essentially puts into question how we measure things and how accurately you can ever get with any one measurement. So again, quick little shout out to that. It is a wonderful documentary. All right, finally, onward to the MSA studies. The MSA studies, in general, it's just one more step in this journey of discovery when it comes to metrology, measuring, and how it's applied to manufacturing and all the different quality organizations that the people who have spent a little bit of their time today to join us for. So these are techniques or tools, as I would describe them, to learn more about your measurement systems. So we've got our set of tools that we're going to be using throughout this, and I'm going to keep kind of referencing that. So you have various tools in your toolbox, and right here we have a simple screwdriver. If I were to give that to any person out there on the shop floor, production line, or even management, they're probably going to have a very good idea of what that's to be used for and what the use of it, and you're not really going to have to give them a whole lot of explanation. So think of that screwdriver in your toolbox kind of like a calibration. Calibration is a fairly simple and straightforward technique of ensuring the accuracy of your gauges. So we're taking an unknown, which is the gauge, and we're going to compare it against a known, which is the reference value. In this case, it could be a set of gauge blocks or standards or something that you're comparing it against. So the whole idea there is we're checking for accuracy. Now, it comes time around spring or fall when you're looking at your toolbox and, man, there's a whole bunch of tools in there besides your handy screwdriver and your hammer and a couple of other common things. Well, you decide to clean things out, shake out the box a little bit. And what you're going to find is when you dump it all out, you discover these crazy looking tools that you've acquired over the years that you really don't even remember what you bought them for. So in a way, these MSA studies that we're discussing, they're kind of like that. A lot of times people approach them as that weird special tool that's kind of hanging out in the bottom of their toolbox, doesn't really get a lot of use, but when it comes time, it's perfectly designed for the application at hand. So each one of those crazy tools on my screen right now, each one of them has a different application. So following along with that, we're going to be talking about 5 MSA studies today: variable R&R, attribute R&R, uncertainty, or commonly referred to as a bias study, a linearity study, and lastly, stability study. So moving forward, the MSA, I've used this acronym quite a few times already, and what that stands for is Measurement Systems Analysis. And all of these come originally from the AIAG, which is the Automotive Industry Action Group. But it applies across many different industries. It's not just for the auto industry. That's just where it began. So this was commissioned by the big 3, Ford, Chrysler, and General Motors. This started around the 1970s, especially picking up steam towards the late 70s with the addition of a lot of white papers. And the big reason why this whole organization, the AIG, came around is because we were losing out, and we're losing out pretty bad to a lot of foreign car productions. If anyone's familiar with Dr. Deming, he did a lot of work over in Asia and China and Japan, and they really took hold of his quality practices, making improvements and focusing on quality and the people. So the big three decided, look, we need to compete and we want to be able to work into our own measurements or improve our measurements. So thus the birth of the AIIG and also these MSA studies. The first official MSA manual was published back in 1990. Currently, we're on the 4th edition, and that was released back in June 2010. My company, we attend the AIAG show every year. It's up in Michigan, and we often ask pretty much every year, hey, when's the 5th edition coming out? And as of this year, I don't really think that there is a to-be-announced date. So beginning, we're going to start up with variable R&R studies, which is pretty much the most common of the 5 that I would say companies, at least companies that I work with, probably engage in. So normally a presentation, a workshop, or even a training of R&R could take 3 hours to even 3 days. I know that Midatoya, they do a fantastic training session all about R&R. They have some phenomenal people that work over there. There's also a lot of other manufacturers of gauges. They also conduct their own kind of walkthroughs all the way through workshops. So suffice to say, we've only got probably about another 35 minutes here. So instead of spending all that time, we're going to sum up. We're going to go over some of the high-level overview highlights and really just talk about the purpose and some of the important things that go into an R&R. So the first R in our R&R stands for repeatability, and in parentheses I've got EV, which is commonly associated as the equipment variation. This is seen when we are observing multiple measurements by the same person using the same gauge, measuring the same part. So what we're going to find is when we do those measurements repeatedly, we are going to get a very simple histogram. What is the distribution of our measurements? So if I've got the gauge in my hand, I'm measuring a particular, maybe I'm measuring the pen cap, I'm doing the length of it, maybe I get 1.2, 1.2, and 1.1. I have just built a very simple distribution of my measurements. The second R in our R&R here is reproducibility. And reproducibility has the parenthesis there for AV, which is attributed to the appraiser variation. Or sometimes, if this is all about fixtures and the humans don't really touch it at all, it could be automation variation. And this is going to be the kind of variance among the different operators. So you might have 3 different shifts. Each shift is using that particular measurement device to measure your goods and products. So first shift, very stable, having good measurements, a lot of good parts. Second shift, a little bit more variability. And then finally the third shift, the measurements are all over the place. They're rejecting things. They're accepting things that they shouldn't accept. We want to know about that because all of that influences your measurement system. So here we have operator A, B, and C. We are taking a look at all of the variation that each one of them has and then comparing between them. So appraiser A, B, or operator A, B, and C, there are differences there that we definitely want to know about. We want to uncover, and this R&R study is a fantastic way to do that. So this definition here, I'm not going to read it word for word. This is the one that comes directly out of the MSA book. The big ticket I want people to remember today is that we're combining the repeatability with the reproducibility, and that's going to pretty much result in our overall R&R or R&R percentage. That's the way that most people are going to be communicating these results. If you walk up to a quality manager or even somebody on the street that's in the know, you could say, hey, I just had an R&R study of 6%. They're probably going to give you a high five because that's communicating to them that your measurement system is well established and it's doing fine. You can distinguish among your parts quite easily. Now, another thing that is also associated with the results of your R&R study is something called number of distinct categories. Now, I've got a couple different examples here, and the one I want to highlight is the bottom one. The minimum required for an R&R study is 5 distinct categories or more. A very simplified way to look at this is if I were to pretty much take a poll of all of the people attending this webinar, and I wanted to identify everybody's height, but I did it in meters or in yards. chances are everybody's measurements are going to fall into one or two buckets unless we have somebody extremely tall on the line. So that's really not enough measurement resolution, and I really wouldn't have a lot of categories where these measurements are going to fall into. If I change gears and I say I'm going to measure everybody's height in inches, that's a much finer resolution or discrimination that I could be using. I'm likely to have far more buckets where these measurements are going to fall into. Now again, that's a very simplified way of looking at it, but it is kind of an overall grade. If I were, again, walk up to somebody on the street and say, I've been taking some summer classes and I just got a B+, without me identifying or talking about any of the things I did during the class, what I learned, professors, anything, that is effectively communicated to that other person, hey, I did pretty good. If I had said I got an F, that's also going to communicate that, look, I didn't pass, I failed. So for the people that are doing these R&R studies, if I say I have an NDC of 0 or 1, they're going to know, hey, yeah, you've got some work ahead of you. So the big ticket here is we want to have at least 5 distinct categories when we actually compute our results. That's kind of our go-ahead. 5 or more, I can draw my attention to the next thing, which is the R&R percentage. So overall, the MSA kind of comes up with this guide for what percentages are acceptable or not. And in general, anything between 0 to 10% is acceptable. Anything between 10 and 30 is marginal acceptance. And sometimes I have to put a little asterisk here. If an auditor or a customer is the one that's asking or demanding that you have these R&R studies completed, they may give you their own percentage that you have to hit. So pay kind of close attention to that. If your customer says we want to have 15% or lower, well, that's the acceptance rate. And then finally, overall, anything above 30% is generally across the board considered unacceptable. Now, what these numbers, this percentages is trying to accomplish is we're saying, look, these variability or the amount of variability is either coming from two kind of main places. Is it the parts themselves when they're coming off the production line, or is it the measurement system? So the lower the number we have here for this R&R percentage, it means that, okay, an R&R of 6%, that's saying only 6% of the possible variation in our measurements is coming from the measurement system as opposed to the parts. We ideally want all of the variation to be coming from the parts. That means we could effectively make our determinations when we're doing our measurements that this is a good part, this is a bad part, or this is an acceptable part, and this is a suspect nonconformance, however you want to define it. So the lower the number, the better here. So when should we do an R&R study? Well, there's a shocking amount of times or opportunities that the guide, the MSA, and a lot of industry standards might stipulate. I'm certainly not going to read all of these, but the big ticket here is usually if you're instituting a new measurement system, you have a new production line, we had to purchase some new gauges, that's a wonderful opportunity to establish a benchmark R&R. Is this measurement system going to be up to snuff to be able to determine good or bad parts? If anything changes with your measurement system, we bought some new gauges or we got some new hires, some new operators, we're revamping how we're doing the production line, new heater, new whatever. Anytime something changes, that's one more variable in your measurement system. But I'll tell you what, I'll summarize this as clearly as I can. When should you do an R&R? It's when you have to. And when you have to is usually defined by some outside source. It could be the next upcoming audit that you're trying to prepare for. You have to supply R&R studies. It could be your management team is coming and saying, look, we need to do this. We understand the importance of it. Or it's coming directly from a customer. Customer says, look, we need to see these studies. I know that Ford and a couple of the other auto manufacturers, if the parts that you're sending them has been measured with a particular gauge, they want to see the R&Rs for those. So it's only something that's going to be growing rather than shrinking. So getting on board now and understanding how to do them can only be a benefit to you and your organization. So why are we doing this study? Well, and again, another summary is it's a method for determining, can this measurement system determine differences among your parts? Can it establish that this part is different from that one and which ones are good or bad? And the other thing I want to bring up is this isn't about accuracy. During an R&R, we're not going to be talking about is the gauge accurate. That is another job completely done during the calibration. R&R is all about, is it capable for the job? If I were to go out to my car right now, we're up in Dayton, Ohio, so it's a little bit chilly. If I were to turn the key on my ignition and the car started, hey, that's like a really simple calibration. I effectively have now just proved the car, the engine, is functioning. However, if I wanted to assess is the car roadworthy, I would have a much longer checklist. Do I have tires? Are there air in the tires? Do I have gas? Is there any safety issues? Do I have seatbelts that function? Is the driver licensed? Is the driver impaired anyway? All of those things combined are going to basically determine whether or not that car is safe to drive, roadworthy, is going to get me to point A to point B. All right, next up is attribute R&R studies. These are for all those go, no-go type of gauges you have lying around the shop. And the big ticket here is that people use the attribute gauges for two kind of main reasons. One, they're quick to learn on, and two, they're fast. If this is not a kind of a critical or final inspection moment, if you don't want to have to spend the time measuring these things with a variables gauge, you can use an attributes gauge to get hopefully the right answer almost every time. Well, these need to be kind of investigated just like any other gauge. Can these users accurately, in this case I'm going to use the word accurately, can they accurately determine which is a good versus a bad part using that go, no-go gauge? So the analogy I like to use, for anybody familiar, there's a show called Deadliest Catch. It's been on for a number of years. The whole idea is there's these crab fishermen off the Alaskan coast, and they are basically risking their lives to be able to catch these crabs, take them back, and sell. Well, they're trying to catch as many as they can, and they actually use a go, no-go gauge, an attribute gauge. So if anybody has seen the show, you might even notice that on their hip they have a little kind of plastic C, and this is the crab gauge in question. So they make different types of models of this to kind of represent different, I guess, breeds or species of crab. But on the left-hand side, we have an example here where a kind of a caliper here is doing the inside diameter, is doing a check to see what that measurement actually is. And on the right, we have a comparison where we're putting a crab up against it, we're putting it across its back, making sure it's the right gender, it's mature, and we're determining, yes, we can keep this in the pot, we're going to take it back, and we're going to sell it. So for them, on that boat, it is very important that whether the experienced users all the way to the brand new greenhorns that just joined the boat, quote unquote, the show, that they know how to use that gauge correctly, because there's a bad choice here where they either reject good crab they could sell, or they accept and put in the pot in the hull of the boat crabs that they shouldn't be accepting. They're too mature, they're not the right species, and that's also going to cost the captain and them money. So what we're looking for here is we've got the no good on the left. These are way too small. They're not mature enough. Hey, we'll catch you in a couple years. And then on the right, we have the giant ones, the keepers. So the gauge in this case is not really going to be that useful when it's fairly obvious. And there's also going to be parts that you're measuring with these go, no-go gauges that, again, are fairly obvious that they're good or bad. The key, though, to performing a successful attribute study is we want to gather these crab or these parts or whatever you're making, and we want to have at least 50% of them kind of fall in the category of good or bad. We essentially want to find some that are going to make it really tough for the operator or for the people on the boat to really spend their time and focus and make sure, yes, I'm making the right call. If they were all extremely too small or way too big, then the study isn't going to be very useful. So this one is a lot more about the operator and the operator's perception when they're using these gauges. So the operators, we've got the experienced, the grizzled salesmen that have been, many seasons on the boat, as well as the new guy, the person that just joined the cast and is really looking to make a name for himself. Now, your actual users, these could be all experienced technicians, people that have been a part of the company for years. They've known how to use the gauge for years, but that doesn't necessarily mean they've been using it correctly. And an attribute study in this case is going to help identify, well, is there reasonable agreement? Are they getting good measurements? Are they accepting the right things and rejecting the wrong things? So the administrator of an attribute study, they are kind of like the ship's captain. They know what's going on. They're going to select, in this case, 50 different parts. That's a pretty common number for these attribute studies. And they're going to establish ahead of time which ones are good, which ones are bad. Then each operator is going to measure with those crab gauges or the go, no-go attribute gauge. And they're going to do this process 2 to 3 times. These will be the replications. So the captain is going to kind of know what the results should be prior to the start of the study, so that way they could compare and say, all right, sailor number 1, he got 98% of the answers right, good for him. Or here's a new person, and wow, this person needs to be retrained. They don't even know what a crab looks like. So some of the different types of results that you're going to be looking at when you do the computations, when you do the computing, is something called cross-tabulation and kappa values. And kappa values is really just a way to visualize by numbers, is there agreement among the different operators? So on the left-hand side, you can see if maybe I can get my pen going here. On the left-hand side, we have the different operators A, B, and C, and in this case, we're comparing each operator to each other. So A to B, A to C, and B to C. So the numbers, 0.86, 0.78, and 0.79, if we look over at the legend, really all of those fall under the excellent agreement. That's a good thing. But really, as an administrator or as somebody who is conducting or leading this study, I really don't know if I care if the operators agree with each other. I am more interested in the bottom half, where it is the operator compared to the reference. So did they make the right call based on what we already know to be true? So in this case, appraiser B, 0.92, that's getting really close to perfect agreement. We definitely want to keep that operator around, or maybe have them train the other people. Operator C, still under the excellent agreement. I don't think we're going to throw them off the boat just quite yet, but yeah, they could definitely improve their technique, relearn the method, and they could actually help us achieve a better goal here of getting closer and closer to perfect agreement with the reference. One other concept in an attribute study is something called effectiveness. And this is the number of correct decisions over the opportunity for a decision. So if I've got 50 parts and I'm having each operator measure it 2 times or 3 times, let's go with 3 times, that's 150 measurements that they could have made a decision on. So the effectiveness here is definitely, I'm going to give the win to operator B. They're 90% effective. That means they're rejecting very few bad crab, rejecting very few good crab, and they are accepting very few bad, meaning we're not losing any money on them, or not that much. All right, moving forward, we still have about another 15 minutes, so I'm doing pretty good on time. These next couple, they actually go fairly quick as well. So next up is our uncertainty studies. And this is really just a way to determine if a measurement system can lie within an acceptable probability of being within what we call the true value, or as close to true as we can get. That BBC documentary on how long is a piece of string will make you question all this, or question the idea of true. But still, what we're looking for is, if we have a known part and we measure it multiple times, are we consistent, and are we consistently close to what we call that true value? So yeah, as my summary kind of statement here says, how likely are you to get to that true value, the correct value? So first, let's think of a histogram. We've got 2 different histograms I'm going to show. We've got the first one. It is tall and thin, and it might be hard to see on the slides. We have listed on here our upper and our lower spec lines. Those are on the kind of left and right-hand side in red, and we have our target right in the middle. So our actual process, our process width, is well inside of our specifications. So this is being considered a tall and thin histogram. We might have a CP here, a process width might be 1.5, maybe even closer to 2. So that's good. Everything is within our tolerances. Now the next example, again, you can see that our Our histogram here is kind of fat and wide. We have our target, we have our upper and our lower. It's all very, very close together and bunched, and we have a good portion of our histogram outside of our tolerances. That's a bad thing. We're not very capable right now. So when I'm measuring, in this case, let's assume that we're measuring these different parts. It's the same part. I'm using this gauge. It's almost a coin flip. It's either going to be way inside or way outside. It's not desirable. Another thing to discuss is the idea of bias, and this is the measurement bias. So the measurement bias is we have our known reference value over here on the left-hand side. All of our measurements that we've taken, they're way off target. We have, in this case, a positive bias. If this is a 2-inch block and I keep getting 2.2, 2.3, 2.2, I'm nowhere near the actual reference value of that block. So that's another problem, and that's one of the things we're trying to identify here on this uncertainty study. So one last example, we are way off target here. Our target is way over here on the right. Our upper and our lower spec lines, again, pretty much barren. No data is falling in between that. And this represents a negative bias. We are much lower than our target. At least we're consistent. So all these measurements are stacking up close to each other. So if it's consistent, we just need to find a way to move it so that it's on target. Again, this is one of the key factors of an uncertainty study. We're identifying, is there a problem with the bias of this gauge at that measurement characteristic? All right, so conducting a study, this is one of the few studies you can bang out really quickly. You just need one person, one gauge, one part, and they're going to be taking multiple or many measurements with that particular gauge. So about 15 to 20 is going to be probably enough of a sample. I'm going to be measuring that particular item, that block, or whatever I have in front of me, and I'm going to be honest with the measurements. So if I take my reading, even if I know it is a block, I'm going to record what the actual measurement was instead of what I think it should be. So in essence, you're going to be plugging in all that data in, and what we're going to be coming out with, based on the formulas in the MSA, we've got two different examples here. If you do have a reference value versus if you don't have a reference value. And the reference value is basically just, is this a block? Can I identify which size this is? Or is this a part that I know what the true size is? So if we don't have a reference value, we can still get our uncertainty value. It's kind of highlighted and circled over here in blue on the right-hand side. The other parts that kind of go into it is we're getting a mean, or getting our average, and we're calculating some sigmas. Sigma R, sigma I, sigma of individuals or range. Sigma of individuals is pretty much good for anything between 2 up to 20. Anything higher than 20, you might switch to the range. If we do have the reference value, the example over in the bottom left-hand side, it'll actually identify, or you can identify, is this a significant amount of bias? So we've identified in this study that our mean is 6.007, and the actual reference is 6. So we're only off by a little bit. It might not impact our measurements that much, especially if maybe we never use this gauge for anything less than 1/10. So the significance here is going to be quite minimal, but it's still nice to know, and it's good to identify that. So the results, what our analysis is, we want to see a low uncertainty value, the plus minus, as low as possible. That represents that we're getting hopefully as close to the true measurement as we can. So if it is higher, that indicates a high probability that your measurements are close to the true value. If you have a very large number, it's almost like putting a ring around your measurement on your control chart, where it could be much higher or it could be much lower. At the moment, you might be just getting one kind of right in the middle. So I have a much better confidence in a measurement system that I've done an uncertainty study on for that particular measurement characteristic when that uncertainty value is as low as it can possibly get. And we're also trying to identify, is there any bias included, either positive or negative? So before I move on to linearity studies, I have to give one kind of note. The steps that I've just described is all part of the MSA guide. There is another method for determining uncertainty, commonly referred to as a budget of uncertainty, or the GUM method, the guidelines of uncertainty measurement. This is far more common when you are a calibration house or vendor. You're the one that has to actually produce those budget of uncertainties, which is a lot more formulas, a lot more math, still very manageable. But the MSA guide is very pretty simple compared to that one. It's really just taking a bunch of measurements, getting an average, doing some sigma calculations, and seeing if you're off target or not. So next, we're getting there, we're pretty close. It's linearity studies. And really, this is just determine is there bias among the operating range of that gauge. So it's really just a bunch of stacked uncertainty studies, but just at different levels of what that gauge can measure. So as this kind of point just kind of notes, we're really just going to be doing it for the different kind of levels of what that gauge can measure to identify, do we have bias here, here, or here? So I've got a couple of example gauges here. I've got a height gauge, I've got a ruler, pretty simple ruler, and then I've got a micrometer. So each one of these has an operating range that we want to work with. So 0 to 24 inches, 0 to 12 inches, or 0 to 1 inch, right? So I would not be using that micrometer for anything larger than an inch. So just a quick review, we're going to be, again, testing for bias. We want to see, are we close to the reference, or as close as we could possibly get to the true reference value of that, or are we way off? So completing a linearity study, we're going to be taking a particular sample here. We've got one of those rulers that I probably stole out of a kid's school book bag. And we're going to be breaking that ruler. It measures from 0 to 12 inches, and we're going to kind of divide it up into buckets of 5. We're going to be looking at, all right, from 0 to 12, let's just divide it, and we're going to be then selecting parts at the 2, 4, 6, 8, and 10-inch marks. That'll be a way to be able to determine, do we have any bias at the low end, the middle, or the high end of what that gauge can measure. So next, we've selected our different parts. Oh, sorry, I moved a little bit too quick on the slide. So we've got our part 1 through 5. Each one of those represents the 2, 4, 6, 8, and 10. And now onward to actually conducting the study. So this is another one where you can pretty much do in one sitting. It just is a lot more measurements than a standard uncertainty study. So we're going to have that one user, one gauge. We're going to have those 5 or more parts to kind of represent the different sizes that that gauge can measure. And then we're going to measure many of those parts, probably about 10 to 15 times each. Once you've computed your results, you can display a chart. The chart could be really helpful in determining, look, do we have any significant bias, and what can we do about it? So I've got a couple of slides here with some various examples. I've got one chart here. We have on the chart, at the bottom, our x-axis is identifying the 2, the 4, the 6, the 8, and the 10-inch marks. We have a set of, in this case, curved control limits, and what we're really looking at to evaluate is kind of twofold. One, we have our mean line, and the mean line is really very close to our y-axis, which is 0.0000 bias, no bias. We want that mean to be as close to that 0 bias line as possible. And second, for each one of the x-axis measurements, we want all of the averages, which are the green dots, to fall well within inside of our control limits. We don't want any that are well above or well below. We don't want any out of control points, essentially. So this one looks really fairly pretty good. The white dots are really just kind of representing, here are some of the measurements that lead into our average, the green dots. If we look over at our y-axis, these are really only going into the hundredths or sometimes even the 100,000s. So it's not that much. We're not off by very much, and it's hugging that 0.0 bias quite well. Great. We don't really have to make any changes, although I'm going to start to watch the 6-inch mark. We're a little bit low compared to the others there. So that's good to know if I need to use this gauge for any 6-inch parts. Be wary. Now another example here is we have the same sort of a setup. We have our ruler, we've got our parts, and this one is drastically different. For one, we do see some points that are out of control, just outside of those control limits. 2, our actual spread of the measurements is really tight. So even though we're off, we are very consistent. It's almost like that histogram that I showed a couple slides back where we're very consistent. The histogram is really tight, but we're just well away from our target. The other thing you're going to notice is that we have a sloping line here. That's indicating that we have some bias at the low end, and we also have some significant bias at the high end. So my 2-inch parts here are coming well below what it should be. So I might be measuring at, 1.5, looks like, every time I measure that 2-inch part. The only thing that looks okay is the 6-inch parts. 6-inch parts are really, really close to being perfect with no bias. So that is, again, a good thing to note. Now I can either try to adjust the gauge to make sure that I get things back in parallel and back right along that 0 axis, or if I just need to lengthen the useful life of this gauge, I can make a special sticker and say, look, this gauge is only rated for 6-inch parts. Do not use it for anything other than that. And the last example, this is another kind of one of those examples where you might be wearing, or there's probably a trend going on with a gauge where at the low end and at the high end, we're seeing significant bias, in this case, positive bias. And again, the only part that it looks kind of off, but it's actually hugging that 0.0 bias line pretty close, and that is the 6-inch mark. So again, same situation, just a different way to see how the results could be presented. All right, we're coming close to the end. All right, so we want on our linearity studies, we want a horizontal line, and we want it to be as close to the axis, the 0.0 bias axis. All right, we also want all of our means, of those green dots, to be well within inside of our curved control limits. We want to find out, is there bias along the length of this measurement device? And if we do, we can either try to repair the gauge or designate it not to be used for any of those measurements that are outside. All right, finally, the last study that we have is stability studies. Woohoo! All right, so gauges need to be checked at regular intervals. This is all part of the conversation about calibrations and calibration intervals or frequencies, how often we need to do it. So a lot of times these intervals, they just come from either the manufacturer of the gauge says, look, we recommend every 6 months or every 3 months, or they've been passed down from the quality department from years ago. So not often do you see that people want to evaluate or double check, hey, do we have the right interval selected for this particular device or this range of gauges? So a stability study is a tool, a technique to be able to determine, look, are we calibrating too often? And are we wasting time and money doing it? Or are we not calibrating them as frequently as we should? We are using a gauge that is susceptible to wear at a different rate than others, and that's also a bad situation. In both cases, you're potentially wasting either time or money. So with the stability study, we're trying to determine, is our measurement system in control? Is it stable? And really, is it stable between calibrations? So that's the big ticket here. If we can predict that this gauge is going to be consistent, we could potentially lengthen our calibration cycle. If we can also predict that, look, it starts to wear well before our calibration or the next calibration, that's giving us good evidence to suggest we need to lower that calibration interval. So from 6 months, maybe we'll ratchet it back to 2 months if it consistently wears in that spot. So a stability study, we have one user, one gauge, one part, and we're going to be measuring that part every couple of days, maybe every other day, maybe in the morning. You just become part of your morning routine, get your coffee, check your emails, you measure that part, and you record the data. So in the end, we're really just looking to build a very simple control chart to identify, is something happening with our measurement system? Is it trending up? Is it trending down? Do I have a point that spikes? This is all things that you want to catch rather than wait until 6 months is over and realize, wow, we've had a problem with this gauge all along. So the results here, this is an example of one control chart, and we consider this a pass. Even though there are some ebbs and flows up and down like any other kind of measurement system, I don't see any points out of control. I don't see any giant spikes that led me to believe that maybe something has happened with the gauge, it's been damaged, it's been dropped, nobody reported it. So I'm going to continue doing my measurements, and maybe I've got another 2 months before it's scheduled to be calibrated. Great, I'm going to keep a close eye on this and wait and to see if there is a problem, if there is any out of control points or trending one direction or the other. Now the next example we have here, you can kind of see pretty closely or pretty right away that we're starting to trend upwards. And right around this point here, kind of around the 5/27/2009 when the study was conducted, maybe something happened. Maybe somebody dropped it, it was damaged, nobody reported it, or this is just naturally when the gauge kind of goes off the rails. It starts to trend in one direction, and boy, if we had another 2 months to go before it was set to be calibrated, we could have caused a lot of damage to our quality department or to our inspection department by using a gauge that is no longer consistent. We cannot predict what it's going to be doing from day to day. So this would be a kind of a shock, and we would want to A, do an emergency calibration as soon as we identify it's trending in one direction, and that's all evidence that we could use to further the idea of, look, maybe we need to ratchet this calibration interval back to maybe the 3-month mark because that's around the time it started to fail. So we're trying to zero in on the appropriate interval where we're not doing it too often and too few. We're trying to get to that Goldilocks zone of we just want to calibrate it right before there's a problem. So the analysis, looking to catch issues before they become huge issues. It can save us a lot of time and money and reworks and checks. And we're also checking to see if we have a stable gauge and we can identify, look, this is the appropriate interval for this gauge. As long as everything stays the same, we're calibrating it only when it's needed. So again, saves us time, saves us money. So winding down, I only got a couple more minutes. I do apologize for running a little bit over. The summary statements here are, these tools, they're sometimes just relegated to the bottom of your toolbox. They are there, they are special, and they can do a really fantastic job. And a lot of times it's only when you kind of bump into them, or in this case, when your customer, auditor, or manager asks. So hopefully you don't look at your toolbox in the same way. All right, now I guess we have a couple minutes hopefully for questions, but before that happens, I also just want to say a big thank you to the ASQ Blue Ridge section. Norville is doing a fantastic job with these webinars, and to anybody that is not an ASQ member or would like to join, please get some information from him. He's a wonderful ambassador for the ASQ organization. So with that, Norville, I'm going to kick it back to you. If there has been some questions that come up, I would be happy to field them as long as people want to stay on.
Okay, Eric, thanks very much. We do have some questions for you. I know time is running a little short. Eric, are you able to see the questions?
I can see there's a chat box. Let me see if I can maybe move that up and maybe I can actually gander at a couple of them.
Okay. The first question that I see being asked is what software is being used in your examples?
The software we're using in the slides is PQ Systems software called Gage Pack. It'll actually do the calculations for you, so you can accomplish these studies without software. You can do it by hand. I've done them numerous times. It's a big time waste. Even when I know what the results should be, I still make mistakes. So having a software like Gage Pack, or really if you want to do it in Excel, that's fine. Other programs, that's also fine. The big ticket there is you hit compute or you let the program do the work. And now you're just focusing on the setup, the conducting of the experiment, and the analysis. So great question, thank you.
Okay, Keith has a question. If part availability is limited, can we use fewer than 50 sample parts for an attribute Gage R&R? How would this affect the statistical relevance of the MSA?
Yeah, great question. There are a lot of organizations, they look at that where it says gather 50 parts and they kind of, are gobsmacked. That's a lot of parts, especially when not every company is making something as simple as a bolt or a pen cap. They might be making large car doors or huge things that are not easily going to be used for a study. The other drawback to an attribute study that some of my colleagues have mentioned is that if you're making consistently good products and that stipulation says, hey, we need to grab some good, some bad, as a quality or as an administrator, you're left with a choice. Do I make bad parts to use in the study? Do I damage good parts? But to circle things back to the original question, is using fewer than 50 parts fine? The short answer is yes. If you've only got 20 parts, go ahead and use them. You could still get useful information out of a study with as few as 20 parts, or even, I don't know if you want to go down lower than 10 or so. But the idea here is the more parts you have, the greater confidence you can basically state when you're doing the calculations, or when the calculations are computed for you. When the sample size is too small, you could be making a knee-jerk reaction when there was only maybe one measurement out. And when you have a slightly larger sample size of something like 30 or 40 or 50 parts, And these studies go pretty quick because it's an attribute gauge. That's why they came up with the idea of 50 being kind of the standard, because that way you have a large enough sample size where the calculations kind of make the most sense, they matter. So there's not really an inherent risk. You could do it as few parts as you really have available, because you're still going to learn some information about your attribute R&R.
Okay, next question. This one's from Bing. Among calibration, Gage R&R, linearity, stability studies, etc., what's the sequence of the above studies to conduct an MSA?
Okay, if I had to design and outline a program or process, calibration is going to be the #1 thing you want to do, and you want to do that first. Because when you're talking about calibrating the gauge, you're bringing it back into tolerance if it was outside of tolerance, or you're establishing that the gauge is measuring fine, it's accurate. I wouldn't attempt any one of these studies with a gauge that hasn't very recently done a calibration, only because the MSAs are really trying to look at the measurement system as a whole, and if the calibration hasn't been done, we haven't established the gauge is accurate already, that's entering in one big variable to the equation. So calibrate first always, and then if you're having to do this regularly, schedule the R&R the next day or the same day or even at least in the same week. That way you could be sure, look, the gauge is okay. We've already done the check on that. Now what we're going to be evaluating is, in the case of an R&R, the people using it, the procedure for how they're using it, the parts themselves, the environment that we're using it in, and you're taking out the gauge variability potentially by quite a lot. The other ones, as far as the order of them being done, I would do a calibration. If I need to do an R&R, then I would definitely schedule it very soon thereafter. If you needed to prove to your suppliers, your vendors, the different people that are asking for these studies, an uncertainty study would be a good next step. And in fact, the first R of an R&R is really the components of an uncertainty study, the repeatability of how much variation is one operator getting. And the last one that I would take on would be the stability study. As soon as I'm done with a calibration, I'm going to start a stability study, and I'm going to be keep doing that every couple of days. I'm going to be recording a measurement, looking at that control chart, recording a measurement, looking at that control chart. And the big ticket here is I just want to make sure that the gauge is still operating, functioning correctly. There's no trends one way or the other. So I hope that answers the question.
Okay. The next question is from Henderson Thomas. At the completion of the MSA study, do you make adjustments to the process producing the item or investigate if the required measurement is valid?
Okay, so when I conduct a study, if I get results that I wasn't expecting, or maybe they're a little bit too high, I'm not really going to be doing any changes to the parts or the shop line where the parts were made. What I'm going to be doing is investigating and taking a look at either the series of charts that you can create from the results of an MSA study. There are X-bar ranges charts, histogram charts, box and whisker charts, essentially ways to visualize what the differences were. And the big ticket thing is whenever somebody has a problem R&R, they get very nervous and they think, oh no, we gotta fix everything. So they might hire new appraisers or technicians. They might completely junk that gauge and buy brand new, more expensive ones. They're gonna change the environment in which all the measurements were done. So we're gonna get a big space heater. We're gonna get this. Essentially, they're going to try and twist every knob available to try and improve things. Now, in the end, you do that R&R over, a couple weeks later, and there's 3 possible outcomes. It gets better, it gets worse, or it stays the same. And given those choices, if you've made changes to everything in the measurement system, you really have a hard time identifying what helped, what hindered, and what didn't do anything. So I always tell people to focus on one of those aspects. Whether it's the equipment variation is too high or the appraiser variation is too high, I'm going to focus on just one of those. So let's go with the example of appraiser variation is too high. That's a pretty good indication that there's significant differences among the measurements between the different operators. Why? As the administrator of the R&R, I'm jotting down notes the whole time. All right, well, operator B, he seems to not be wearing his reading glasses when I see him wear those every other day. So I wonder why, and maybe that could have impacted the measurements. Another more common thing is that nobody's been trained or properly trained or retrained on how to use that gauge or how to use it with that part. Maybe there has been no training, there's no method defined. So a lot of times you'll uncover problems in the quality system and in the measurement system, and then you're going to attack that, create a plan. You're going to implement that plan, and a couple weeks later you're going to do the R&R again, and guess what? The question of whether it got better, got worse, or stayed the same, you're going to be able to point the finger and say, look, we instituted this project, we made improvements here, we retested, and now it's better. Great, that worked. If it didn't work, great, we're going to change gears and investigate a different angle of it.
Okay, it looks like we have one more question here from Henderson Thomas. If you use MSA studies for a service industry, you compare yourself to others in that industry, but where can you find out how others are performing?
That is a good and also a very difficult and challenging question, mostly because if it's a service industry, if you're providing something other than what we would call kind of a tactile hard part that you're going to be measuring with a potential gauge, it could be extremely difficult to try and emperor and the elephant the results, meaning trying to figure out a way to get the results to kind of work inside of this form. So the biggest thing I would probably say, and this is kind of a note to Norville as well, he mentioned that he had found me through social networking. To be able to give this webinar today, I would say that that's probably going to be the best way to find data or results in your industry, is hit up chat rooms, forums, be a fly on the wall in as many groups and organizations as you can find, and likely they're going to be sharing different data, different pieces of information. Not necessarily that you're going to be able to throw into an MSA study per se, but at the very beginning of the slides today, Norville was sharing the webinar, how it started kind of slow and then we've slowly grown, and that's data that people are willing to share. So the service industry, as far as measurements and what you can record and what you can actually do a study on, that could be a pretty big challenge for anybody. And hopefully my tips of just networking, being available, reading up, attending forums is going to be a piece of good advice for you.
Okay, it looks like we have another question here. This one's from Adriana. Is there any particular recommendation concerning to testing for bias when we are dealing with variables in a bimodal distribution?
I don't really have any good answers for that one. I've certainly seen one or two occasions when you have a bimodal distribution, which is probably fairly uncommon, or I hope would be fairly uncommon with a measurement device. And I'm assuming that most people out there probably know what bimodal means. It just means there's potentially more than one Hun. It's a non-normal distribution. I don't have any real set advice. I don't want to steer you wrong on it. I'm trying to think, Adriana, I might know of a couple of other industry people. If you can send either Norville or myself an email, I'll try and get you in contact with one of them that they might be able to give some more additional information, but I certainly don't want to steer you wrong on any answer that I might have given.
Okay. Let's see. Doesn't look like we have any other questions in the chat. Just want to have one last final reminder here. On Thursday of this week, it'll be our last webinar for 2017. It is the Changing Role and Opportunities for Quality Professionals with Data with Kimberly Porter. That'll be starting at 12 noon Eastern Time. And let's see, do we have any others at this point? Looks like we have no further questions. We've run quite a bit over for today. Appreciate those folks who are still on here with us. We'd like to thank Eric once again for giving this talk today. Really appreciate your willingness to do this for us. And also like to thank those of you who came online with us today. We're always happy to have you with us, and we look forward to seeing many of you possibly on Thursday. Until then, we'd like to wish everybody a good rest of the day, and hopefully see you on Thursday. Until then, goodbye for now.